Okay, thank you very much for coming along. Today is a recording because we have the public holiday, so this will be posted for you and you'll be able to watch along. Okay, so last week we left off here at the example. Now we've been looking at both the cumulative distribution and the CDF, so the PDF and the CDF. So the density function, so we had the exact values, the probability of x equal to something, and then we had the probability of x being less than or equal to something, and we were learning to use those. We introduced the idea of variables, and so we were just in the middle of that. So the cumulative distribution function, the CDF, is the one that we're looking at in terms of what it looks like as a graph. So the CDF for the graph is very simple in the sense that it's this one. Okay, so what would happen? It would add up. We get add up and accumulate and accumulate and accumulate, and so it'd become increasing in its graph form. Okay, so this is the one that looks like this. Okay, so the next thing, of course, is the use of this. We've had a little bit of a look at using these to do computations, and so we progress that. All right. So for an interval, okay, for an interval, so we're looking for 2 and 3. So that's our 2 and 3. But we have to take into account the cumulative nature of what's happening with that. So everything below 2 is no good. So that's everything below here is no good. So we don't want that. So in effect, when we take a look at Px is less than 2, it includes all of those things. So at some point we have to subtract the 1 and below. Okay? But it's not the 2 that we want, it's the 3. So in order to put the interval together, and please, this is important because just pulling this together can often be quite difficult for students in the first instance, and I think I made that point during the lecture before. So what we have now is from 3, because this is where we're looking at 3, okay, but 3 will go all the way down to 0, so we want to pick that up, but this time we only want 2, so we're going to have to subtract everything below 2, which is 1. Now notice this, please, because this causes confusion for students, and it only happens in the binomial distribution. Okay, so the discrete random variable is a discrete distribution, and so notice that we're taking the one below. Okay, I'm just making that point for you for this reason that I pointed out earlier. So it's very straightforward then to put them into a computation, and what we're looking at is simply 0.999 minus 0.9. So now we're taking away everything below 1 and including 1. So if we subtract all that, then we'll get 0.0522, or if you like, in JSON parlance, 52 thousandths. Okay, so 52 thousandths. Alright, so for our expected values, we can use this technique then to do computations with regards to our statistics, and that's why we're using them. Okay, so our expected values, in this case here, is our mean. So we've looked at that before. So the mean is our expected values. We need to change that language so that we don't get confused when we see one and the other. So for n equals 5,000 students, let there be a number of courses which a student is randomly assigned 5 possible courses. So any one of 5. 5 from any number n, 5 from any number n. The number of students allocated and the probability mass function is given in the table below. Okay, so the PMF, the probability mass function, that's this guy, isn't it? Okay, so the PMF for each of these is given in this form. So we're just making sure that we're aware of the difference, that subtle difference. So the PMF is the exact, remember that was the word that's often used, exact for PMF, as opposed to the cumulative, which is picking everything up. So all that's happening here for the allocated courses 1 to 5, and these are the allocations. The probability then becomes a proportion, and so we've got 740 over 5,000, and so what we find is that 740 over 5,000 is 0.148. Okay, and then we go on to the next one, and you'll see that these are very straightforward. Okay, they're just going to be used in the sense that we sum them. So if we look at our expected value, we're going to have the product of these, the product of these, the product of these. All we're going to do is add them. Now, isn't it interesting? Well, I'll get to that point in a moment. So we'll do 1 by 740, and then we'll sum to that 2 by 2000, and then we'll sum to that 3 by 960, and we'll sum to that 4 by 800, and so on and so forth. Now we're finding x bar, so we're going to divide by the total, which was 5,000, and we get an average of 2.664. So the expectation was 2.664. Now, interestingly, we have summed that way in our computation. Okay? And in a way, another form of the same thing is just to add these together. Okay? We can just sum all of those. So 740 over 5,000, if we were to do it this way, 740 over 5,000. Oh, what am I doing there? Oh, split the fraction. Is that all you're doing? Well, why are you doing that? Just to show you the different form. That's the split fraction. It's the same thing, and so on and so forth. Okay? And so we get the final one, 500 over 5,000, and you get the same thing. It's just a different form. And sometimes it's expressed that way, and it's hard for students to pick up that they're actually the same thing. This is the split fraction form, and it's using the probabilities being summed together, multiplied by their course allocations. So it's 0.5, 0.4 plus 0.6, etc., etc. So you can think about that. So what I've just described there, of course, is exactly what I've put in summary here. So we can just multiply them and sum them and multiply them and sum them, and that's what I did on this line here. This was this line here. Okay, so expectation is our mean. The expected value often looks like this. So that's our expected value. Okay, so it's 1 times 0.148 plus 2 times, and we've just done that. We're repeating ourselves, plus 5 times 0.100, and we notice all of the division and everything else is put in, so 2.66. It's the same result. So expectation, okay, is the sum in this particular example from I equals 1 to 5 for our variable and its function value. So it's a bit more formal than what you did at high school, but nevertheless it's the same thing. Okay, so fairly straightforward. Now for expectation, that means we can also know that there I've put it formally for you. So the expectation is the mean, so we don't want to lose sight of that, and it's expressed in this form, and that's just the thing there. But sometimes it's harder to pick up the function value for the PMF means that you're taking the proportion as a probability. So if you think about what I just said there, we're taking the proportion as a probability. So each of, I see probability elements multiplied by xi, okay. For variance, a similar kind of thing. For variance, you've got a rather complicated thing, but not really. Work out the expectation and square it, then subtract that from the ex squared function, which is given here. Okay, so in this case here we would work out the expectation and square it. This one here is the sum, but this time there's a square. That's the only difference between the two. See, it's not there. There it's a 1. Here it's a 2. And that goes into the variance. Okay. So the standard deviation is the square root of the variance, which is the square root of s squared, of course. So very straightforward. Alright, let's see if we can use these equations as we have been already for our discrete random variables. This time, what are we looking at? Well, we've got exact values. So we've got our exact values, okay? So our expected value, or our mean, if you like, is the sum from I equals 1 to n for our value multiplied by our proportion, okay? And so if we go through and we do the first one, 0 times 0.6561, so that's the first one, tick. Then we're going to sum that with 1 times, oh there it is, 2916, and so on and so forth until we get to the bottom one, 4 times 0.1 of a thousandth. And so we get an expected value of 0.4. The mean is 0.4 for this particular data set. So the variance then requires us, and we're just getting into practice of using our random variables and their probabilities to help us. Oh, that's what we're doing. We're using probabilities to compute mean. Who knew? Oh, really? Okay. So that's what we're actually doing. We're using probabilities. That's great. Probabilities aren't such a big scary deal after all. So we can use it also to express our variance. There's our mean that we just did, but this time we'll square the whole thing. So if we go through and do this guy here, we'll get 0 squared times 0.6561. I'll skip a few. 4 squared times 0.111, and so we'll get that 0.52. So 0.52 minus the mean that we worked out squared is going to be equal to a variance of 0.36. So this then helps us work out, and we take the square root of that and we work out the standard deviation, and that helps us to understand how steep it is. Okay, so we're using probability to compute means. Oh, you always make us wait, Jason. We were talking about expected values. What were expected values? You did make the point that it was a mean up here, but then it became rather cumbersome, didn't it? We didn't realise that what we're doing is we can use probabilities to compute means. How good is that? So that allows us to do that. That's just a repeat of that question. I don't know why I've left it there. So we'll go to a new one. So how would we do this one? Well, we just multiply them. Sum them, multiply them. Very straightforward. So the expectation or the mean for this set of data is just taking the random variable px equals, has a probability, sum that with px equals 9, has a probability, px equals 10, has a probability, px equals 11 has a probability, px equals 12 has a probability, and we do the sum of all of that and we get a mean of 9.98. An expectation, we've got to do this part. All we're doing in this case is we're squaring. That's the only difference. Squaring, okay. 12 squared, and so we'll end up with, from that we can then work out our variance, okay. So our variance becomes, using probabilities to work out our mean and variance. Oh, that's why probabilities are so tied up with statistics. But the way we're using it here, that's not hard. I can do that. That's wonderful. That's not terribly difficult. Squaring that mean that we just worked out, 101.1, 9.9 squared. So those summing equations are not terribly difficult, and of course they lend themselves to computation. So 1.5 variance, so our standard deviation is the square root of the variance, which is the square square root of 1.4996, 1.2246. Oh, so we use probability to work out our statistics. We use probability to work out our statistics. Oh, okay, so if we can work out the probability, we can work out our statistics. All right, so that's what's going on. Okay, that's very good, very helpful. Oh. So, of course, some of you will recall your experiences with the binomial theorem, and it's part of what we do here as well. So we'll continue on with the binomial distribution. So the binomial distribution need not be the scary thing that you recall. Let's just try and keep our feet on the ground and do it in a less confronting way. So the binomial experiment satisfies all of the following. They're independent identical trials, two possible outcomes, which we describe as success or failure. Then we think about the probability of success. We're more comfortable with that. That's P. The probability of failure. Now this here, I want to say, is the complement. Okay, so if we take the complement of a success, we'll get a failure. We take the complement of a success, we get a failure. There's another thing we'll do with that. We're interested in x equals the number of successes, and so that's the random variable and the number of successes. So if we toss a fair coin 20 times, that is, it's got a head and a tail on each side. Let the successful event be that the head appears. So the number of heads in 20 tosses. The probability then, if we're given as 0.5, the complement of the probability of 0.5, and n equals 20. So very straightforward from an experimental point of view. So let's think about this with some other less familiar settings or contexts. Can these be binomial? They have to be independent. They have to have two identical trials, independence, and only two possible outcomes. So let's see what we can get here. Bit morbid, this one, Jason. 90% effective poison is given to 10 rats. What's the probability that exactly 9 of them die? Okay, so that we get that. We're looking at the language, and you're starting to get stronger and saying, oh, well, that is that. Okay, that's density PMF equals 9. That's the one. We know that. Yep, we know what that means. Okay, that's good. But it just wants you to say, can it be used as a binomial? So we're looking for, are they independent? Well, does the impact of one rat affect another? No. So we can say that they're independent. So that's a tick. Okay. The next thing in the list is, are there two states? Oh, this is a bit harder to swallow. Yeah, there's two states, unfortunately. They're alive. And then there's a morbidity, so I'm not going to say the other word. You can do that. So yes, we can use the rat experiment as a binomial model, using a binomial model. A laboratory has 8 machines. They break down independently 5% of the time, so we're given that. We're also given a proportion of breaking down. What's the probability that more than one of the machines break down at a particular time? So can we answer that question by using a binomial model? So we've got our two states, running and not running, so broken down, running or not running. So that leads to independence, so we've got that. So that's good, and we've got two states, so yes, we can use this in a binomial model to work that out. A narrow neck bottle contains 3 green and 5 black. The bottle is shaken thoroughly and 3 olives are rolled out one by one. What's the probability all 3 are green? Now, can we use that in a binomial situation? So if we've got our bottle, our flask, okay, and in there we've got 5 black ones, which I'll draw like that, and 3 green ones. Okay, that's what basically we've got, and they get tipped out, and then we might get a black one. Oh, and then we've got to do the experiment again. Okay, and this time we might get a green one. Oh, well, first of all, they're not independent. because what happens in the experiment 2 is direct result of what happens with the other one. So unfortunately we can't use the binomial model to describe that particular problem. So we're just keeping tabs on some experiments lend themselves to certain types of modelling, and so that plays a factor. So as we develop our knowledge and skills in that area, it'll become more apparent to us. Alright, so the binomial distribution, we say that x takes a binomial distribution. This can be shortened to x follows as a binomial distribution, and this bit here is usually follows as, and they're often expressed this way. So look out for these because they'll describe different distributions. This is saying that the random variable x is following as a binomial distribution. So we need to be able to read the language, the equations. This is shorthand language for us to understand that we're doing a binomial distribution. So the binomial equation is something that will be familiar to you. N choose x, you might want to just make a little note of that. N choose x. So I think I've put it down here, it's been put down here for us as well. So N choose x, and so we've got this probability. Now why are we doing probabilities? Because we compute our statistics. Don't lose sight of that. We're computing our statistics, okay? So we've got this N choose x. Now N choose x I've given by definition here, so it's quite straightforward. And our factorials, that's the one with the exclamation mark. So for example, 3 factorial would be equal to 3 times 2 times 1, and that would be the value of 3 factorial. So those computations can be done by hand, and they can be done by computer or by technology. We can use our technology for that. So with a binomial distribution, if we have a look at a binomial distribution with 10 and equals 10 and a probability of 0.5, we can go through and we can compute the probability for a particular random variable. Okay, so this is quite an interesting contextual problem using this idea. Alright, the probability of successfully landing a plane using a flight simulator is given as 0.8. Oh, thanks for that. So P equals 0.8. 9 randomly and independently chosen student pilots are asked to try and fly the plane using the simulator. So N equals 9. Well, that's very good. What is the probability that all 9 of the student pilots successfully land the plane using the simulator? Well, I would hope that the probability would be quite high. So x equals 9. I would hope that would be the probability. And according to our definitional equation, it's n choose 9. The probability raised to the power x, the complement of the success, n to the minus x. If I put that into its definitions, and of course you know I'm a bit long-winded in the way I develop all of these for your benefit, because if you don't know why things are, how are you going to find problems or correct errors? Okay, it's all very good to be able to program. It's another thing to be able to do the maths. So we've got x is 9 and n is 9. So we've got 9 factorial. So these guys are 9. They're all 9s. So we've got 9 factorial, 9 factorial, 9 minus 9 factorial. Then we're doing this bit here. The probability is 0.8 to the power 9. Then this bit here, the complement. And so we get, now that's 0 factorial. So we get 9 factorial over 9 factorial times 0 factorial. 0 factorial is in fact 1. 0.8 to the power 9. The thing that was in the brackets is to the power 0, so it's gone, it's now 1. So that wasn't a very onerous computation really. So 1 times 0.8 to the 9, because 9 factorial over 9 factorial is just 1, so that whole thing was 1. Okay, so we've got 0.9, or 0.8, sorry, I changed that. You're not here to tell me that, so good thing I caught it. Times anything raised to the power 1 is 0. And so we get a probability of all 9 students landing the plane approximating 13%. Goodness gracious, I'm a bit scared of using those pilots. I would have hoped that would have been a better percentage, but ooh, so that's a very good use of, oh dear, that's going to be a bit of trouble, isn't it? So what's the probability that at least 8 students successfully land the plane? So there's at least 8, so that's the language now, so that's at least 8, okay? So at least 8 is going to, if we look at the miscellaneous statistical parts, there's a table there, and it gives you the language matched, and that's at least 8, so it's around that way. So that's a skill in and of itself, okay, and that can be found in the usual place. I think I've demonstrated that a couple of times, so I'll just press on with the video. So what we have is the probability of 8, and so we can go through and do all the computations again, and we'll get a probability of 0.0319, which is approximately 30%. 30% of students of 8, but that's not what we want. We want at least 8, so we want that one, and there's 2 ways to do that, okay? So at least 8, we can sum the, because there were only 9 students, n was 9, we can sum the uppermost parts in the table. So when the random variable is 8, we can sum that together with the random variable that's 9, and that will give us the probability 0.019 plus 0.1342. So that was previously, so I'm just going to box that because that's an answer, but there's another way to do that, and I mentioned it before, and that's to take the complement. So for the binomial distribution, you'll be taking the probability of the fail. So what we're going to do is the one below. Ooh, we did that before. Okay, the one below. So if we go and compute the PMF, remember this is a PMF, we could go and compute the PMF if it's not given to us. Now, of course, I'm more generous than that. I'm going to help you out. 792. And so that becomes something. Now, it turns out that they're both the same. So you can do that by hand. 9, 10, 11, 5, 3, 4, 4, 3, 6, 2, 1 minus 0.5, 4, 6, 3, 2. So we get 4, 3, 6, 2. So we get that probability 2 different ways. This is taking the complement. Please take notice of that because it'll solve some of your puzzles later on, particularly where you have to turn this around. I haven't taught you anything. This is very important now. I haven't taught you any technique or computation using greater than other than to use the exact values and add them up by hand. So there's no, that's the P, remember the CDF is that way. Sorry, I better get that right. The CDF is that way. Okay, so when we get problems of at least where the inequality is around the wrong way, we have to do a conversion. The way that we do that conversion is by taking the complements. Okay, very good. So if we can take the complement, otherwise you'll be adding them all up. So if you're adding them all up for a large n, that could be problematic and error prone, but this way we've got another method. We can use the complement. Alright, so what's the probability that at most 2 pilots? So again, the language is coming in. The language is at most 2 students. Okay, so we've got to think about the at most. Again, you can go to the part in the lecture notes, and we're looking for stats miscellaneous. In case you missed it, I better just quickly pull it up for you because I've referred to it now a couple of times. But if you go to Canvas and you go to our maths and modules and statistics, I'll just do the student view so it's not confusing. And we go down to resources, the miscellaneous here. If we go to the miscellaneous and we have a look at probability notations, okay, probability notations, and that's a LaTeX table I did, and the probability notations, and we're looking for at most, so we're the length or probability. So at most means a CDF. At most means a CDF. Very good to know. Okay, at least is the complement of the CDF. At least is the complement of the CDF. So at most is the one that we're looking for. So it's a CDF. So we can use the cumulative distribution idea. Now, having said all of that, we've landed that, but let's answer the question, which is the hard part. Now, I'm not going to cruel you. I'm just trying to help you. So what's the probability that at most 2 student pilots fail? All right. So if we've got no students fail, 1 student fails, 2 students fail, then we can say that's the same as saying of our 9 students, 7 or more succeed. So the question was given to us in the form of a failure, a Q, whereas we're now phrasing it, this was our Q, and we're now phrasing it in terms of P. Okay, so if we now say 7 or more, we can do the one that's not so helpful. Oops, that's around the wrong way. The probability of success for 7 or more students can be done 2 ways. First of all, we can take all of the exact density function values and sum them. Okay, that's easy. That's one way to do it. We can do that quite straightforward. Okay. The other way that we can do that is we can take the complement of the one below it. So turning around, as soon as I take the complement, watch what I do here. X is greater than or equal to 7. Here, X is greater than or less than. Oh, that's a PDF. That's a CDF. A cumulative distribution function. A PDF on my brain. So this is 1 minus 0.2168. Now that was given, okay, from the cumulative functions, and so both of these will end up being the same answer. Okay, so that is 7382, or approximately 73.8%. So in order that we understand the probability that at most 2 student pilots fail, then at most 2 students failing is 73%, which is a bit easier to digest, isn't it? That's a bit better. So again, the probability idea helps us to compute our statistics, and it's not something that we should be concerned about. Once we get the hang of how to use them, is very, very straightforward. So X is a binomial random variable with parameters N and P. Then our expectation or our mean, okay, if it follows as a binomial distribution, there's our abbreviated language, and all it is a product. Very, very straightforward. Okay, so our expectation, how good is that? Working out our mean, all we've got to do is, that's a multiplication out of primary school. There's our mean, our variance. We don't have to go through that whole rigmarole we went through before. We can just use the equation. Wow. Okay, so now we have some shortcuts to help us compute our statistics. Now you know why statisticians love probability. Oh, very good. So hopefully that is something that you can be somewhat at ease with in terms of how it's progressed. Okay, so I've just formally put that. It's the same problem. It's the same problem, just in a formal sense. Okay, so we can do this in R. We can do the same thing in R. And so all R does is request of us a particular, making sure that we put the right values in. So for a binomial distribution, there's 2 versions of the binomial distribution. One of them is D binomial. The other one is P binomial. Now it's just the way R is organised internally in terms of library calls to have those names. But they use the D and the P consistently across all of the density and distribution functions, across all of them. So if it's got a D in front of it, could be exponential, could be normal, I think I've already demonstrated that for you, it's going to be the exact value. That's the one we're talking about. So x follows as binomially distributed with those two parameters, then we can compute that using this call. If we get this call, we'll get that value. Okay? And we're looking at the PDF, the density function, which is exact. Okay, that's the exact one, isn't it? There it is. That's the exact. Look at this one. The question's asking for greater than 5. So what do we need to do? Well, we can't do that because that's not a CDF. It's not a cumulative distribution function. Look, I'm training your eyes to look at these outputs because that's what you're going to get tested on. Not the programming so much. You've got one thing you've got to do for me to send me some example. You could send me this. This would be good enough. But what this tells me is that this is a CDF. Okay, so how do we get from this thing here, which is at least, to this one here, which is our CDF? Our CDF call. We need to get that one into that form. So how do we do that? What's the big trick there? So even though we've got the software, if we run the software call like this, what are we going to get back? We're not getting that back. We're going to get this back. So that's not the answer to the question, is it? So what we've got to do is we've got to say our probability, there it is for our random variable. Why is that important? Because we're kind of going about it the wrong way, or not the wrong way, backwards. Oh, but I want to get this guy. Oh, I see. So how do I get that guy? I've got to take the, what's the phrase? I've got to take the complement. Okay, and as soon as I take the complement, the sign turns around. Okay, so now I've moved from not having a function to having a distribution function that matches. Okay, so in this case I can read it off or I can compute it either way. And so that I have to do this bit manually. This is only the second part. That's only this bit. So in your computations for R, you have to do that manually. So that's 0.36897, which is approximately 36.7%. Okay, so when we're using R, if we're it depends very much on the question. Okay, find that one. All that, if we look back at our, that's the one that goes up. At least 3. Okay, so this one was asking, find the probability that the random variable is at least 5. How do we do that in practice? Well, we have to take the complement, and then we can use the CDF. So we've got both forms here in front of us, the exact form and the CDF form, and so we just need to be mindful of that. Okay, it's a very, very big page in my view, I guess. There's a few of them that I point out to you, and I guess that's one of them. Alright, let's see if we can continue on using the idea. I'll let you tinker and play with that, and we'll be having a look at that in the recorded lab as well. Okay, an article in IEE, we're not excluding ourselves. Computer applications in power discusses an unmanned watching system that detects intruders using videos and micros. Under snowy conditions, the system detects intruders 50% of the time. Whoops. So our probability is 0.5. Our N is, now, what is the probability in a particular trial of the system with 10? So that looks like N equals 10. Will detect at least 7. So there's the language. So you've got to go and grab that at least. What's it telling us? At most, so it's not the CDF. Oops. Okay, we're going to have to use this, and that inequality x is greater than or equal to 3, and then we're going to have to turn that around. So in actual fact the question is asking us this. Okay, at least. So there's two ways to do this. We can sum for all of them from 7 to 10. Just using our exact distribution function. Very straightforward, but it's laborious because you've got to go get all the computations. Oh, that could take you some time. Or, if you like, we can take the complement of the one below. Why do we take the complement? Because it does. I see. This is now a PMF, which is much easier to, we can compute that using R, that bit, just by using the previous slide. And so that's a bit easier to do. Okay, which is 171.9 thousandths, which is approximating to 17%. Okay, so not too bad. If we want to continue on answering questions, then all we need to do is use one or two of the methods. Very, very straightforward. What is the probability that the system will detect fewer than 4? So to put that into the maths, so again this is the language issue that comes up in statistics. The language and probability is what the statistics are doing. So less than 4. Okay, now we haven't encountered that one quite. Where's the equal sign? Well, it's not there. So that would be all the probabilities going from 0, wouldn't it? If we would do it the manual way, we'd do it that way, and then we would go 3, and then we would finish that one. Or we could use the PMF, but we need to be careful. If we use the PMF, because we can compute the PMF, we can't use 4 because it says fewer than 4. So we need everything below 4 so we can take everything there. Okay, so that's the PMF below or fewer than 4. Okay, so if we do the computation for the binomial distribution using those things, we'll get that. So it's not that complicated once you get the hang of it, and hopefully you're feeling that as well. Alright, so what I'm going to do is I'm going to make 2 videos. This is the finish off of lecture 3, and I'll be making another video for lecture 4, which is this week's lecture of course, but this was to finish off lecture 3, and hopefully you're feeling that, and you can look through that yourselves. Alright, so thanks very much for coming along for this part. Lecture 4 I'll post soon. Public holidays, wow.